So good evening and welcome to the return of the in-person SLAC Public Lectures. Look, I thank you for being here. We've had lectures before where this auditorium was full. Today there's a lot of room for social distancing, but hopefully as the pandemic recedes, we'll see crowds here again. And really, I thank you folks for being the pioneers and coming. I should say the speakers are very enthusiastic about having real people in front of them. So we thank you very much for being here. So today's lecture will actually be a really fascinating one. The lecturer is Cyndia Yu, who's a graduate student at Stanford and working with the KaiPak Institute here at SLAC, and also with the technical people who are working on quantum devices, quantum sensors. And this is part of the 60th anniversary series of public lectures, where we want to emphasize new capabilities, new technical capabilities of SLAC. And one of the important ones is using actually advanced devices, quantum sensors, to understand the universe better than is possible with those old-fashioned classical devices that one used to use to do astronomy, chemistry, biology, etc. And Cyndia is right in the middle of it. She's here doing her PhD. She was an undergraduate in Arizona. She's come here to do her PhD, and she's building these things, and she will tell you all about it. So Cyndia, thank you very much, and we look forward to a very interesting lecture.
Thanks. All right, mic is good? Cool. All right. Thank you all so much for being here and for missing the Warriors game to be here. So a bit about me. The earliest memory I have of sciencey things was seeing the Intel Pentium fab. So I was born and raised in Chandler, Arizona, which is mostly a suburb of Phoenix, so very hot and very dry, and I think is best known for being the site where Intel does a lot of its fabrication. So if you touched a personal computer in the late 90s or early 2000s, it probably had an Intel Pentium chip. And the first memory I have of vaguely sciencey things was getting to actually do a tour of that when I was, I don't know, 7 or so. But after Arizona, I moved out to Boston for college, where I learned what snow looks like and that I really thought physics was awesome. After college, I hung out in New York for a bit, studying mostly economics research and operations research. And then I decided that physics was actually amazing. So I came out here to Stanford, where I proceeded to forget what snow is like. And I'm doing my PhD now in the physics department, studying, as Michael said, quantum sensors for studying the universe. And one of the cool things about being a grad student in this field, sort of pun intended, is you can put your sensors in very interesting places. So this is me when I was installing some of my work at the South Pole. So I am interested in measurement. How do we know things about the universe? We know things about the universe because we see them. We see them happening. We, even as early as people really can remember, we observed things about the world around us, and we found patterns. We found patterns in when the sun rises and sets, when the seasons change, when, when the sky gets dark, then suddenly water falls out of the sky, these sorts of things. And we started getting better and better at being systematic about making these observations and trying to use them to make predictions that allowed us to use those predictions to govern our lives, to figure out, based on the movement of, for example, things in the sky, when we should wake up, when we should plant the crops. And for the most part, we've just been getting better and better at these observations. We've gotten devices to be able to help us see really small things, and that allows us to look at things like cells and try to understand microbiology. We've gotten things like telescopes that help us see really far away, and then we can see things like stars and planets, and try to understand the movement of the celestial bodies in the solar system and beyond. And it turns out that we can also observe things that are not just directly in front of us in light. And we do that because we can use the pretty cool fact that magnets repel and attract each other. So you've probably encountered a fridge magnet. You can push it against a fridge and it attracts. If you put two magnets together, in one direction they attract each other, in the other direction they repel each other. And similarly, electric charge repels or attracts depending on its sign. So here the balloon static is pulling this guy's hair up. You can try this at home if you want. But this means that we can now sense things like whether there's a magnetic field present. We can sense things like whether there's electric charge present. And so we can start to unlock phenomena like we can understand that this like big bright flash in the sky has something to do with electricity. And that's pretty cool. And in the 1800s, people also started to notice that it's not just that we can observe magnetic fields and we can observe electric fields, but we can observe them changing because moving charge, so current, makes magnetic fields. If you just have some current running and you put it near a compass, the compass will shift. And conversely, moving magnetic fields creates current. It creates changing charge. So if you put these two things together, you have a changing electric field creates a magnetic field, and then this magnetic field is changing and that creates an electric field again. And then you have these things, the electric field and the magnetic field propagating together as waves, and they propagate at the speed of light. And that's awesome. And it turns out that we can now use this fact to send and receive information about light and about electricity and magnetism. So at the end of the 1800s, Hertz was playing around with a system where he just created these giant electric sparks. And then across the room, another receiver that he had, this antenna on the right side of the screen, had also created sparks at the same rate. And so this was telling him that he was sending information about the electric field on one side of the room to the other side of the room. This electric field information, the changing electric field, was turning into a magnetic field that was propagating and then being received again as electricity that he could see. They asked Hertz what the use of this invention was, and he was like, I don't know, probably not much. We now know that he was super wrong, because this in some sense was the defining discovery of the 19th century, because our entire modern society is built on the idea that we can catch waves of light of all different lengths and all different sizes, and turn it into electricity or magnetism and observe that again. And light turns out to come in more than just what our eyes can see. You can also have light in the radio. So these fields are really, really spread apart. And so we call that longer wavelength, and those are very low energy fields. And you can also have that the peaks and the crests of these electric and magnetic fields are really, really squished together. And so that's really high energy. Those are like X-rays or gamma rays. And this is essentially like how your car radio works, is that some radio station is beaming out this information and your car antenna picks it up, turns it into an electric field that is vibrating, well, that is vibrating a speaker, and that's how you hear it as sound. You can also do something like Wi-Fi. So, put your information into light waves at 2.4 gigahertz or 5 gigahertz, or whatever frequency your Wi-Fi band is, and then an antenna in your computer catches it and turns it back into the information that you can interact with. And we can also do this with telescopes, catch big light waves from the universe and turn that into electricity and use that to reconstruct what's happening out in very distant galaxies. So what sorts of light might we want to measure? You know, things very far away galaxies, astrophysical objects. We might want to measure very small things, take the light from microscopic or even like subcellular objects and turn that into electricity or magnetism that we want to measure. And so we can start to ask questions like, are there magnetic fields in, you know, people's brains? Is electricity a part of how human cells interact with each other? That's pretty cool. But obviously, I'm not going to send you home after 10 minutes. People also started noticing this weird observation. So they knew that if you shine light on a piece of metal, you start getting charge. You start getting something that you could like charge a battery with. Electrons start coming out, so units of charge. And what do you expect to happen when you change this light? So if light is a wave, you expect that a bigger wave, so bigger amplitude, like should kick out more energetic charge. And you can, this sort of makes sense, right? Like if you have a bunch of beach balls on like a pool of water and you shake the pool of water a lot, then the beach balls have way more energy. And if you shake the pool of water like not very much, then the beach balls have less energy. And if you have a bigger frequency, so you like shake it faster, then you expect to kick out the beach balls faster. And so you might have like a faster current. But when they did these experiments, what they found was that it was exactly the opposite. So a bigger frequency, so the faster you shake it, the more energetic the beach balls, and the bigger the amplitude, the more current, the more electric charge is coming out. And also they found that there's some cutoff frequency, so some speed of shaking at which you just get no current at all. So what's happening? We now call this the photoelectric effect. And it's essentially this idea that light is not just a wave, but you can imagine it like a particle. So the difference between the left and the right here is the color, is the frequency. And if you have light that is too low a frequency, it means that it's not energetic enough, and so it can't kick electrons out of the metal. Whereas if it's a higher frequency, then it's actually displacing the electrons. And if you have bigger amplitudes, so shaking it harder, that means you're just throwing more light out. And so you are pushing more electrons out and you get more current, but you can't change how energetic they are. And also, as you turn this down, you can't get half an electron. So there's a certain amplitude that you can't get anything out, and there's also a certain frequency that you can't get anything out, because eventually you get below 1 electron and eventually you get not enough light. And so I used to say that, I said before that light is a wave. You know, you have this white light and it's made up of all of these different colors, but also light is a particle. And this weird particle wave duality is a key feature of quantum mechanics. And so it gives us some pretty neat results. So the photoelectric effect is one of them. Another one is this idea of interference. So you've probably encountered interference if you, for example, throw a couple of rocks into a pond, you see these ripples. And depending on how the ripples line up, they might interfere constructively. So the waves come together and make a bigger wave, or they might interfere destructively, so they cancel each other out. So if you shoot light at this, what we call a double slit, so a wall with just 2 holes in it, you can get bright parts and dark parts, depending on whether the light is interfering constructively or destructively. But what do you expect to happen if you throw an electron? An electron is a particle, it's an object. So you expect to just get a big pile behind each of the holes, right? But when they do this experiment, it turns out if you just shoot a beam of electrons at the screen, you also get an interference pattern. So it's not just that light is both a particle and a wave, but things that we thought were particles also have wave-like behavior. And so these pretty cool facts of quantum mechanics, this particle wave duality, this idea that everything is quantized, this idea that the electrons in some sense look like they're taking both paths at once in order to create this interference, are key hallmarks of quantum mechanics. And we can exploit these features to create all sorts of cool quantum sensors all around the lab. So here at Stanford/SLAC, we have quantum sensors using a variety of different technologies that are all reliant on this fact that quantum mechanics is really weird, and that allows us to sense really, really small signals. And we're unified in general by this theme that we have to use quantum mechanics to get to fainter and fainter signals. Like, we have already gotten to the point that our classical detectors just don't work well enough anymore to see the things that we want to be able to see. So what sorts of things are that? You might want to look at elementary particles. So what is our entire universe made out of? You might want to look at dark matter. So we know that the sorts of matter that you and I are used to, the stuff that we're made out of, is only about 20% of all of the matter that's in the universe, all of the heaviness, the stuff. And we have no idea what the rest of it is. So we're trying to figure that out. You might want to try to understand how chemistry works on a better level. In particular, it's really hard nowadays, typically, to watch chemical reactions happen at the individual molecule level. And you might want to ask the question, like, how does this chemical process unfold? And can we watch it in real time? You might want to understand biology. So you might want to ask the question, for example, what is blood made out of? Like, what is hemoglobin made out of? If we understand better how hemoglobin works, then we can understand how to create artificial blood. But it's currently extremely difficult to measure the structure of the hemoglobin molecule and create that artificially in the lab. And we might also want to ask these huge questions. So, like, where did the universe come from? Lots more. And I'm going to be focused on this question right here of the birth of the universe. And so the thing that I am interested in measuring is what we call the cosmic microwave background, or I'm going to say the CMB. And the CMB is a baby picture of the universe. So if you think of our present day as, you look out into the night sky, you see these stars and these galaxies. If you look back farther in time, you start to see, baby galaxies and then baby stars. And the first stars started turning on maybe 200 million years into the age of the universe. And before that, we know that the universe had some hot dense state. There was some sort of Big Bang. And the CMB is the last light from that. And so it's about 14 billion years old. And we've already learned a huge amount from it. So it's from the CMB that we know things like what the universe is made out of. We know the shape of the universe. We know its age. We know a little bit about where the universe came from. It was the fact that the CMB exists at all, that there is this like afterglow of this hot dense state, that we knew that there has to be some notion of the universe having a beginning. But the experimental challenge is this thing is behind everything else in the universe. So if we want to detect it, and we want to detect it here on Earth because satellites are very expensive, you have to look past the clouds, you have to look past the atmosphere, past our solar system, our Milky Way galaxy, other galaxies, all the baby stars and stuff, to this thing that is 14 billion years old and very, very cold. It's about 3 degrees above absolute zero. So we use a quantum sensor to do this. We use superconducting sensors. And to understand what superconducting sensors are, we have to take a detour through what non-superconducting things are. So resistors, taking a detour back out of the CMB, we are trying we use a technique called superconductivity, which means that resistance goes to zero. So what does that mean? I found this picture on the internet. I think it's very cute. But you can sort of think of moving current through materials as having these three components. So you have this yellow guy, the volt, who is the size of the electric field difference. So he is trying to push electrons through. And you have this guy, the amp, who looks very worried, probably rightfully so, because this is the amount of current. So how much electrons are flowing. And this guy in the cowboy hat is the resistance. And he is essentially, how difficult is it to push electrons through a material? So if there's a big resistance, that means that he's really strong, he's pulling really hard, and so there's very little flow of electrons. But if it's a very small resistance, that means he's not squeezing very much, and it's very easy to push electrons through. It's very easy to push current through this material. So normally, you can think of some things like insulators, where it's very difficult to push electrons through. The chemical structure is mostly that all of the atoms in this material hold on to their electrons. All of the molecules like to hold on to their electrons, and so there's not much room for other electrons to squeeze through this material. In metals, what usually happens is there's this lattice, and electrons kind of flow around. So there's this very easy, very neat grid, and when you try to force current through, they bounce around, but there's like generally a path that they can get through. And so we usually think of metals as being pretty good conductors, which means their resistance is not very high. What happens though if you take this structure and you cool it down? So normally temperature, higher temperature corresponds to more movement. So there's just all of these atoms like kind of shaking around, having a dance party, and the electrons are trying to squeeze their way through. And as you cool things down, they start freezing a little bit, don't move as much. And so the electrons have a little bit of an easier time going through. And so usually for materials, as the temperature drops, the resistance also goes down. So the dude with the lasso is just pulling less hard, and the electrons are having an easier time. But at zero temperature, this generally comes to some finite resistance. There is some amount that the electrons still have to weave through all of this stuff that they have to travel through this material. In superconductors, though, at some temperature, the resistance just goes to zero. So it's not even like the lasso is really big. It's like he's not there at all. And so all of the current flows through. None of it gets lost to collisions. None of it gets lost to heat. And in fact, the current in principle can go forever. There are people who have started current going in superconducting loops, and it's been going for decades. And there's no reason that it should stop. So what's going on here? So if we go back to this picture of the metal atoms arranged in this lattice, and when you try to push current through, the electrons are zooming around and they might bump into other things in the lattice. As you cool stuff down, the atoms shake less. And so now you have this kind of ordered grid. And now you have this electron that wants to come through. And remember that I said that charges either repel or attract depending on their sign. So an electron is negative sign, and these metal cores are, when it comes through, the metal cores are positive and they want to come a little bit closer to the electron. They prefer to be closer to the electron than anywhere else. And so creates these little pockets where things are a little bit more positive than they otherwise are in this lattice. And so when another electron comes through, it prefers to join it. And so they actually become friends, and they travel together. We call these friendships Cooper pairs, and they move around much more easily than individual electrons. But the magic of quantum mechanics isn't just that they move around more easily or that they're friendships or they're friends. Friendship is magical, but it's not a quantum effect. But it's that they move around so easily that the resistance goes to 0, because Cooper pairs, they don't travel like particles anymore. Now they move like a fluid, they move like a wave, and they travel through this material without really even seeing that all of these metal atomic cores are there. So, superconductivity, we want to use it to measure the cosmic microwave background. We're trying to measure the leftover light from the Big Bang. This is the most recent all-sky picture from the European Space Agency Planck satellite. It's very old and it's very, very cold. It's about 3 degrees above the coldest temperature possible in the universe. So how do we measure it? It's a good approximation when you want to measure a thing. First, you have to catch it. So we take this light that's traveled to us and we put it in a bucket. We catch it. And now we want to understand, what is this light? And the main thing that we want to understand about this light is, how hot or cold is it? What are these slightly hotter and slightly colder patches that you see in this picture? And so if you want to measure how hot or cold this light in our bucket is, you use a very good thermometer. So where do we get a very good thermometer? We can use superconductors, because it turns out that this transition to 0 resistance here is not just instantaneous, but it's this very, very, very sharp transition where the resistance versus the temperature changes a lot, but not instantaneously. And so if we get light coming in from the cosmic microwave background, it comes in, it heats up our bucket a little bit, it heats up our material a tiny bit, we will see a huge change in resistance. So these are the sensors that my experiment uses. They are fabricated by NASA Jet Propulsion Laboratory. And what you can see here is, you can see this giant piece of metal, and that's essentially our bucket. That's the thing that we're using to collect all of the light after we've gotten it into our telescope. And we are now trying to measure a big change in resistance that came from a small change in temperature. And these transition edge sensors, as we call them, are so sensitive that they can measure single photons. They can see a single particle of light come in because it's such a big change in resistance. So now we have this change in resistance. It's quite large. And that allows us to read things out as a big change in current, because you can't just measure resistance. You have to see how much it suddenly allows the electrons, the green guy, to flow through your material. How do we measure a big change in current? We use a SQUID. Okay, not a sea creature. A SQUID is a superconducting quantum interference device. And this is the circuit diagram, and I'll walk you through it. But I first wanted to show you a pretty picture of the SQUIDs that we use. These ones were made at the National Institute of Standards and Technology out in Boulder. And it's this really cool kind of cloverleaf pattern that you have here. So what is this doing? Remember how I said that, remember how I said that current, you have a giant change in current, and this current wants to go through this. If you have a current going through a superconducting loop, it could go forever. But instead, what we have are these X's here. So these X's are very, very small breaks in the loop. And electrons will go across, because they're a wave also, right? They're not just a particle. So when they hit a wall, they don't necessarily stop. With some probability, because they're a wave, they'll go to the other side, they'll tunnel through. Quantum mechanics is amazing. They'll tunnel through and they'll make it to the other side of the loop. So in this version, I have 2 different breaks. Sometimes you can have 1, depending on the kind of SQUID that you're using. But now you have some scenario where current can actually get through this loop and come out the other end. But what's amazing is that the path length, so how long the different arms are of this loop, depends on the magnetic field that's going through the middle. So you can sort of now think of this as another version of our double slit experiment, because the current could go through one arm, the current could go through the other arm, but depending on which path length is longer or shorter, you suddenly can create an interference pattern. You can have that the two currents interfere constructively, so it gets really big current on the other end, or you could have that they interfere destructively and you get no current out on the other end. And so you get huge changes in how much current comes out of this device, depending on the magnetic field inside the loop. And what's pretty amazing about this is that the spacing in between these things, so how much magnetic field creates one of these fringes, is insanely small. So SQUIDs are the best magnetometers in the world. They can measure something like 100 million times smaller than a fridge magnet in magnetic field. And so they are sensitive to, even the smallest changes in magnetic field from for example, neurons firing in someone's brain. So people use these things for magnetic imaging, among other things. And at this point, we can just connect these superconducting devices, which need to be kept super, super cold. And so we have to put them in these refrigerators to keep them superconducting. We can now connect them to room temperature electronics. So these are ordinary in the sense that you don't need to keep them in a fridge, but they're still super sophisticated. Lots of people here at SLAC spend all of their time building different versions of these. So this is one of the ones that I work with. We keep it in an electronics rack. For those of you that like playing with electronics, you might recognize a spectrum analyzer and a vector network analyzer. And we keep this in a corner of our, in this picture, fairly clean lab. We try to keep it cleaner. So let's put this all together. So we have this transition edge sensor. Ours is made by NASA, but lots of people make them. And we are using it to catch the light from the CMB or whatever very small signal you're trying to measure. And this light comes in, it gives you a very big change in resistance, and you want to measure that as a big change in current. So what we do is we take a lot of these sensors and we connect them up in these arrays or cameras full of these things, and we conscript a very friendly postdoc named Ari in this picture to connect them together. So he is using a technique called wire bonding. It's kind of like soldering for those of you that play with electronics at home, but instead of connecting the two wires in front of you, use a microscope and ultrasonic power to bond the two ends of your microelectronic devices together. And so now that it's connected to the SQUIDs, we can hook all of that up to wires and put all of this into a telescope. So here at SLAC, here's a team that includes Zish, who's sitting in the back, who put these things together into different experiments. And we take these experiments and we take them to, in our case, the South Pole. And from there, we let it look at the sky and measure the early universe. But the South Pole and measuring the early universe are not the only things that you can do with quantum sensors. So SLAC quantum sensors also go down into mines. So they're shielded by hundreds of meters of rock to get away from all of the stuff in the atmosphere in order to go to the very quietest places on Earth to try to hear things like whether dark matter is passing through or whether neutrinos, these super, super, super tiny neutral charge particles, what are they doing? We also try to put these sensors, for example, in the high mountaintops of Chile to try to measure early galaxies, to try to measure early stars, and also maybe even the echoes of the Big Bang. We also, just other building that way, we'll put these quantum sensors in our beamlines here at SLAC. So we have these ultra high energy electron beams, X-ray beams, and we collide them with various samples in order to try to image them. And we can use these quantum sensors to make better and more sensitive images of all sorts of chemical processes, all sorts of biological processes. So where is quantum sensing going? There are a few frontiers in quantum sensing that people in the community are involved with, especially here at SLAC. So one of them is new detector concepts. So a couple of things that I'm excited about. So backing up, if you, this is a circuit called an inductor capacitor resonance. So inductors and capacitors are essentially different ways of storing electromagnetic energy. So inductors store them in the form of a magnetic field, and capacitors store them in the form of an electric field. And so if you hook them up together, you'll find that they actually ring because the energy is just sloshing back and forth between being stored in the electric field and being stored in the magnetic field. And how fast it rings, so its frequency of ringing, depends on how big the inductor, how big the capacitor are. And so what we can do is we can build a device that gets an inductance from these Cooper pairs, so these pairs of electrons that are friends. And what happens is when light comes in, a photon comes in, it can actually break a Cooper pair, destroys the friendship, it's very sad. And the inductance changes. And so you suddenly get that this bell that was ringing at one frequency starts ringing at a different frequency. And so then you know that light must have come in somewhere. Another cool concept that relies on quantum mechanics is using qubits. So you might have heard of quantum computing and how it is the hot new thing. And essentially how quantum computing works is in classical computing, you have these bits in your computer. They're either 0 or 1. But in quantum computing, in the same way that light is both a particle and a wave, the current travels through both arms of the SQUID loop, you can have that the state of the bit is somewhere in between 0 and 1. It can be anywhere on the sphere. And qubits make great detectors because now you're not just sensitive to signals that flip you between a 0 and a 1. You're sensitive to anything that moves you anywhere on the sphere. So you can have something, you can now have a detector that gets you like slightly from the top of the sphere to like halfway. And that is information that you can actually read out as different. And that wasn't something that was available to us before. And so here's actually a cool picture of all 3 of the sensing technologies I just told you about, the inductor capacitor one, the transition edge sensor, and the qubit all in one fridge. Another way that we are pushing the frontiers of quantum sensing is this notion of multiplexing. So for a lot of our experiments, we want to have many detectors. These detectors must be superconducting, so they have to be cold. They have to be low enough temperature that you can actually see the transition. And so that's usually below minus 270 degrees Celsius. Our electronics that we are hooking up to, the thing that actually stores the data to the hard drives that we then analyze, is at room temperature, so 25 degrees Celsius. And so you have to run all of these wires between something very cold and very hot. And wires also bring heat with them. And also they are kind of a pain sometimes just to manage. And so multiplexing is a way of reducing both just the pain of putting these things together and the temperature difference, so how much you're connecting the hot thing to the very cold thing by putting many, many detector signals on as few wires as possible. So this is a picture that is reading out about 15,000 detectors, and technology that we're working on here at SLAC can reduce that to just these 4-ish pairs of wires in this fridge. And so, yeah, the wires that you see here are capable of reading out probably 10,000 sensors at a time. And so that's dramatic reduction in the number of wires and also in how difficult this thing was to put together. And similarly, when we're talking about scaling up superconducting sensing, it's not only just the wiring, the multiplexing, but we're also just trying to make ways to make more of them. So it used to be kind of a pain because you'd have to make every single superconducting sensor and hook it up, and that's a lot of work. And so borrowing from the advances that a lot of them actually came out of Silicon Valley here, of fabrication techniques for computers, for computer chips, you can actually lithograph entire arrays full of sensors now. So this one is out of Argonne National Lab. These are a bunch of transition edge sensors that have now just been printed onto a silicon wafer, and it gets put through many of the exact same processes that the computer chips in your phones or in your personal computers are made out of. And so we're working on this here at SLAC. This is a picture I took of myself in one of these very shiny wafers last week. And one of the cool things about making these things is you can put your own logos on them and create art. And finally, in addition to developing many of the techniques to do this, at SLAC, we're actually, in just the next building over, building a brand new superconducting nanofabrication facility. So most nanofabrication facilities use a bunch of different metals, depending on whether people are trying to make regular computer chips or whatever other devices that they're trying to make. But superconductors don't play nicely with normal metals. They get contaminated and then they don't superconduct anymore. And so having a dedicated facility for just superconducting devices is really important to making high quality devices and also making them at scale. So currently the clean room is mostly just an empty room, but it's a very clean, big empty room that is being filled with instruments in the coming, like this summer. I've started seeing crates for instruments come in. And so we're going to be mass producing wafers for all sorts of experiments in the next couple of years. So as I've alluded to a bunch of times, SLAC really is a new leader in this field of quantum sensing. We have people from doing everything from coming up with these new device concepts and testing them, figuring out how to take this idea and turn it into like how to actually get information out of it and how to actually connect it to a real experiment with all the other wiring. People who are figuring out how to do this more than just once. People who actually run the experiments, put this thing all together, get new data out of it and try to understand what other things do we want to do? What other experiments do we want to run? What new capabilities do we want to have? And then we have people who also come up with new goals for where we can put these quantum sensors. Now that we have quantum sensors, what sorts of things can we measure now that we weren't able to measure before? And people are working all over this. It's not really so much a circle as it is a giant interconnected web. But I couldn't figure out how to make PowerPoint give that to me very easily. So now it's a circle for you. I mostly focus on the electronics and system integration side, as well as running experiments and analyzing data from them. My friend Katie here, who is also happy to answer questions after this, actually works on designing and simulating new devices and characterizing them. And she also runs her own experiment. Hers looks for dark matter, a type of dark matter particle that people have thought of. And if you search Stanford Q-Farm, quantum fundamentals, architectures, and machines, this is a new initiative between Stanford and SLAC that is aiming to bridge all of the different quantum efforts between Stanford and SLAC. So this is quantum sensing, but also quantum simulation, quantum computing, all of these new frontiers that are unlocked by quantum mechanics. So in summary, quantum sensing enables this brand new sensitivity across a huge range of science goals. We can now study things like biological processes, things that previously were too sensitive or too faint for us to be able to study classically. We can study dark matter, we can study fundamental particles, we can study, we can make movies of chemical reactions happening. These are all things that quantum sensing has unlocked for us. And there's a huge number of these super interesting but super weak signals that are worth searching for, that are worth people spending time on. And the last thing I'll just say is that this field is an exciting one. There are lots of new detector concepts emerging, and there are lots of new experiments to run. So with that, I'll take questions. Thank you so much for having me.
Cyndia, thank you very much. So this is a nice room for questions. All of you have in front of you a microphone. If you push the red button in the center, you can talk. What I'd like to do is have you raise your hands and I'll call on someone, so we only have one microphone going at a time. So questions, please. Yes.
Hi, Cyndia. Thank you so much for your presentation. Really love the sensor working with SQUIDs. So powerful. Whoa. Speaking of power, what kind of bandwidth can that combo work at?
That's a great question. So the question, I think Zoom probably heard the mic anyways, but the transition edge sensor SQUID combination bandwidth. So for those unfamiliar, bandwidth is essentially how fast of a signal can you see? Like how quickly can you see differences? And there's a bunch of different things that set the bandwidth of the system. Usually we prefer to run so that the transition edge sensor is the dominant thing that controls the bandwidth. You don't want the SQUID to control your bandwidth, because then there might be a detector signal that you can't see anymore because the SQUID isn't fast enough. So the transition edge sensor, the bandwidth is set by essentially how good this bucket is at changing temperature. So how much the resistor actually responds to incoming light. And depending on the application, that sets how fast you want these things to run. So for the cosmic microwave background, we don't actually want these things to run very fast. So we tend to run in, the hundreds of hertz sort of range. But for people doing pulses, they're trying to actually measure like the energy of a single pulse, like an X-ray pulse that's coming from the X-ray beamline here at SLAC. They will run up at like several gigahertz, not gigahertz, sorry, several kilohertz up to several megahertz of bandwidth.
Anyone else? Please. Oh, just turn on the microphone with the red button.
Hi. Yeah, I'd be fascinated to know a bit more about how this technology could transform people's lives, quantum detection, development. Your example about artificial blood sounded quite interesting. Are there any more examples of what this development could mean for the ordinary man and woman on the street?
Yeah, that's a great question. I mean, anything that requires measuring an incredibly small signal is interesting. So one of the first applications of the technology that I worked on, this multiplexing technology, was trying to understand how to do better security. So if you want to, for example, detect whether or not people are violating nuclear non-proliferation treaties, you're trying to figure out whether very, very small amounts of nuclear material is getting into, for example, the atmosphere or the water around some place. And these are really, really, really small amounts of some nuclear material. And so it's very hard to detect with classical methods. But if you have a huge number of sensors looking for them, these very faint signals, then that enables you to detect much more easily and much earlier whether nuclear materials are coming out. The artificial blood example is a former office mate of Katie and mine who worked on that. So trying to understand the structure of hemoglobin, like how it actually binds to oxygen. Usually it's basically impossible to actually image the structure of hemoglobin in the laboratory, because any sample of blood that you create, you usually have to either freeze it or dry it out to put it through the X-ray beamline here, but then you're destroying how the hemoglobin is actually working. So trying to figure out ways, and then you're also like bombarding it with X-rays. And so trying to figure out ways to much more sensitively measure this thing with much higher precision allows you to figure out whether the iron is binding to the oxygen in these different ways, and therefore how to possibly create artificial ones. Yeah, essentially anything that you can think of that you would want a very sensitive sensor for, and especially a non-invasive one. So because all of these things are collecting light, collecting information and not sending out signals in order to get information, it's also hugely useful for just like non-invasive imaging.
For the transition edge sensors, what is the resolution for those sensors? Or rather, what's the minimum step size for discerning different signal levels?
That's a great question. The resolution of a TES depends on the material that you're using. So some of them can see single photons, and some of them obviously need to have several photons in order to be able to see them. It really depends on the application that you're looking at.
But the ones you're making for the CMB see single microwave photons.
The ones that we're making for the CMB can see microwave photons, but we usually don't try to resolve individual photons.
So, did you make any progress on the dark matter discovery thing?
Yeah, Katie, where's dark matter?
On the dark matter side?
Oh,
Yeah, so I guess I can speak very briefly about the dark matter side. So basically, all the physicists know about dark matter right now is that we don't know what it is. So there's a lot of wide unexplored parameter space, and with experiments, even ones that are really sensitive, like the ones that we're building with these quantum sensors, you still have like a lot of places to search, and you actually have to search kind of very slowly because you're waiting and integrating and like building up these small signals. And so while there are actually there are many new experiments coming out for different types of sort of dark matter that they're looking for. So the ones that I particularly work with are looking for a type of particle called the axion. We're still like very much in the stages of like a lot of these experiments like coming online and collecting data. And so while there haven't been any groundbreaking oh, we found dark matter, there's a lot of like parameter space that's being sort of probed and swept through, and I guess just a lot of progress is being made, but it's hard. It's easy to look at sort of the range of possible dark matter candidates that we haven't ruled out yet and say how are you ever going to find it? But I would say that there's a lot of new experiments coming online that are doing very cool things.
I
So
think
what
the
are you
other
looking for though?
So in the case of the axion, which is the experiment or the type of particle that the experiments that I work on look for, there's actually sort of theories proposed that there's this incredibly small interaction between the dark matter particle and standard model electromagnetism, which is Cyndia talked a lot about electromagnetism and how that's something that we can measure with these quantum sensors. And so you're looking for this incredibly small electromagnetic signal for the axion at a particular frequency that's related to the mass of the particle.
So another question related to dark matter. Is there a reason why I guess many scientists and physicists believe that we should prefer the idea of dark matter over something like modified Newtonian dynamics?
Sure. So that's a great question. Modified Newtonian dynamics is essentially the idea that our law of gravity doesn't actually work, and there's just a very small change to it, and that should give you dark matter. But it turns out that as far as we can tell, dark matter, so first of all, the CMB tells us that there is something massive, some that actually exists that we can't detect. And it's actually incredibly difficult to reproduce the CMB using just modified gravity. So I usually say, I don't believe a modified gravity scenario unless it also predicts the CMB looking the way it does, and essentially none of them do. The other answer is just modified gravity doesn't really solve the dark matter problem because you need to explain why it works only on certain scales. And for every single scale that we have ever under the law of gravity, it exactly matches what we expect. And so if dark matter is just modified Newtonian gravity, why is it only interacting at these scales that we can't detect? And how does that scale map onto the thing that we observe, which is this very large phenomenon?
Can I just add?
Yeah.
So modified Newtonian gravity was originally introduced to explain the rotation of galaxies. And so you introduce a parameter that works at the scale of galaxies. But now we have a very large number of probes of dark matter. So we see it in galaxies, we see it in clusters of galaxies, actually the largest ones observed. We see it in the CMB, which is coming from 14 billion
years ago. And the simple model says it's a particle, it interacts under gravity, it produces all the phenomena that we see in nature. And the modified gravity, it only explains a tiny part of that. So it's just a much more compelling theory at this moment. Of course, you know, it would be nice to discover the particle, but
Yeah.
unfortunately, all these theories work whether the particle weighs essentially the mass of an electron or 10,000 times smaller or 1,000,000 times larger. And so there's an enormous range to search. And, you know, I'm a theoretical physicist. Every theorist has their own favorite value within that range. So most of us will be disappointed, but eventually I think we'll find it.
Yeah.
Okay. Please, Becca.
Thanks very much for your presentation. So if we were to say that at the origins of the universe, different points in space, quote unquote, update at different times, would we be able to detect that with quantum sensors of this resolution?
That's a great question. So it's true that different parts of like what we are seeing when we talk about the cosmic microwave background is we're seeing the light that came off of the hot, dense state of the universe that is being released as the universe cools down. And so that light is constantly changing because as time evolves, the part of that hot, dense state that's cooling down that you can see is going a little bit further back. And unfortunately, that really happens on timescales that are much, much longer than a human lifetime. So if we were to start an experiment and just run it forever and ever and ever, and compare the map that we get now with a map that we get in like, you know, a few million years, it will be a different map. But the point that we try to make in when we study the cosmic microwave background is usually that we don't care like what that specific part of the sky says, but we care on average. So cosmology is trying to understand the universe as a whole. And so we're trying to understand like on average, what does the sky look like? What is it made out of? And what does that tell us?
Let's take one more question and then go in. Anyone? Yes, please.
What is so special about the 300,000 years of the CMB? The earliest light that we receive from the CMB was 300,000 years, right?
Yeah. So that's a great question. The CMB, we say, is about 300,000 years into the age of the universe, and that we know is how long it took for the universe to actually cool off enough so that the light got released. So the early universe was super hot and super dense. So it was kind of on fire everywhere. Like you should imagine the early universe is like the sun. It was just on fire and it was so hot that photons, so particles of light, couldn't actually escape it. They would just like bounce and run into a charged particle and get absorbed and then re-emitted. And it like, a crazy fact is the photon, a particle of light that is born in the center of the sun, it will take about 1 million years to get all the way out. And so the early universe was the same way, and then it was cooling. And eventually it got so cold that it became neutral, so it was no longer charged particles, but instead neutral hydrogen mostly. And photons don't like to bounce off of, don't like to scatter off of neutral particles. So instead of scattering off of the neutral hydrogen, it instead just prefers to stream out into the universe. And so that's what we call the CMB, is the thing that bounced off that last charged particle and is now scattering towards us. And so that 300,000 years is approximately how long it took for the universe to cool off enough that that was possible.
Well, look, Cyndia, thank you very much. Very illuminating lecture. Okay, we will be back here in person in early August for the next of these public lectures. Please look for the announcement. Those of you who are not on our mailing list, talk to me or talk to Carmen here to get on our mailing list and you'll get the announcement. And again, thank you very much for coming. We're restarting the tradition of having these lectures on a regular basis every couple months, and we hope to see you again. So thank you very much. Oh, I should say one more thing, which is that Cyndia and Katie will be out in the lobby once we get everything cleaned up, and we can answer more questions for a little while. So if you want to wait out there, we'll be out there soon.